Hello and welcome to this revision session for AQA A-Level Physics, Paper 1, in the topic of further mechanics on the concept of simple harmonic motion. So in today's revision session, if we've been successful and we've learned today, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics, and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? Well, when completing your work in this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than the right hand side, and in this left hand side section write down your working out and answers to the questions in the revision session. When you're doing this, make sure to write your answers in full sentences and show your full working out. Whilst in the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. Now, how should you be revising for AQA A-Level Physics? Well, the first step is to learn the key facts. Use revision guides, class workbooks, student prep notes, the textbooks to learn the key ideas of the course. Now, you may wish to make mind maps or write out notes yourself. The second step is to test yourself. Use things like Caboodle, Seneca, student knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then finally, practice exam style questions. So use exam prep books, homework books, supervised study books, additional workbooks to answer exam questions and mark your own work. Now you may wish to download your own exam past papers to do this. So your 3 steps should really be, firstly, learning the key facts, then testing yourself, and then answering practice examination style questions. So, when we're doing this revision session today, we'll be looking at 2 types of questions. Firstly, general check questions, which are basic questions designed to probe your understanding of the key concepts of the topic. Then secondly, we're going to be looking at assessment point questions, which are past paper examination questions which will mimic the type of questions found in public examinations. So, let's have a go at some of these general check questions. So the first question says, state and justify whether the following oscillations show simple harmonic motion. A basketball being bounced repeatedly on the ground. So pause the video now, then unpause the video when you want to go through your answer. This is not simple harmonic motion, as there is a constant acceleration of gravity towards the ground, but not on hitting the ground and when hit by the player. A guitar string vibrating. So pause the video now, then unpause the video when you want to go through your answer. Right, the answer is yes, it is simple harmonic motion, as the restoring force is directed towards a point and is proportional to the displacement from that point. The next one, a conducting sphere vibrating between 2 parallel oppositely charged metal plates. So pause the video now, then unpause the video when you want to go through your answer. This is not simple harmonic motion, as it travels with a constant acceleration towards each plate and then suddenly reverses its directional velocity on hitting the plate. The pendulum of a grandfather clock. Pause the video now, then unpause the video when you want to go through your answer. Well, this one is simple harmonic motion, as the restoring force is directed towards a point and is proportional to the displacement from that point. A person jumping on a trampoline. So pause the video now, then unpause the video when you want to go through your answer. Now, when the person is not in contact with the trampoline, the restoring force is equal to their weight, which is constant. Now, their value of weight doesn't change even if they jump higher and change their displacement. Now, the restoring force on a person therefore is not proportional to the distance from equilibrium, so therefore it does not fulfill the conditions of simple harmonic motion. Now, the next one is a cuckoo in a cuckoo clock emerges from a fully compressed position to a fully extended position in 1.5 seconds. Calculate the angular frequency of the cuckoo as it emerges from the clock. So pause the video now, then unpause the video when you want to go through your answer. So, how do you answer this question? Well, we know that when we're working out our value here, our angular velocity is equal to 2 pi over t. Now in this case, t is going to therefore be equal to 3 seconds, because one complete oscillation is when it returns to its original position. So it takes 1.5 seconds to go fully out, and then another 1.5 seconds to go fully back in. So it's 2 pi over 3, which is 2.09 radians per second. The next question says, a mass of 55 grams is suspended from a fixed point by means of a spring. The stationary mass is then pulled vertically downwards through a distance of 4.3 centimeters and then released at t equals 0. The mass is observed to perform simple harmonic motion with a period of 0.8 seconds. Calculate the displacement x in centimeters of the mass at time equals t equals 0.3 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, the first thing we need to work out is omega. Now omega is 2 pi over t, so it's 2 pi over 0.8, so it's 7.85 radians per second. Now the general equation for displacement in this case is x equals a cos omega t. It's cos because it's starting from maximum displacement. So it's 4.3 cos 7.85 times by 0.3. Remember, it needs to be in radians for this to work. So we get minus 3.0 centimeters. Now the negative value indicates it's displaced on the other direction or the other side of the equilibrium position from the direction on which it started at. The next question says a simple pendulum is released 30 centimeters from its equilibrium position and completes one complete oscillation every 1.5 seconds. Calculate its displacement 6.2 seconds after it was released. So pause the video now, then unpause the video when you want to go through your answer. As in the last question, omega is equal to 2 pi over t, so it's 2 pi over 1.4, so it's 4.5 radians per second. Now as the pendulum was released at its maximum displacement, we use the cosine version of the displacement equation, x equals cos omega t. Pop in all the values and we get minus 0.27 meters. Remember, the minus indicating it's on the other side of the equilibrium position. The next question says a simple pendulum oscillates with simple harmonic motion with an amplitude of 15 centimeters. The frequency of the oscillations is 6.7 Hz. Calculate the speed of the pendulum at a position of 12 centimeters from the equilibrium position. So pause the video now, then unpause the video when you want to go through your answer. So we know in this case we're given frequency, so omega is equal to 2 pi f, so it's 2 pi times by 6.7, so it's 42 radians per second. Now the general equation for velocity or speed is v equals plus or minus omega times by the square root of a squared minus x squared, so it's 42 times by the square root of 0.15 squared minus 0.12 squared, so our answer is 3.8 meters per second. The next question says, a toy bird is suspended on a spring from the ceiling. It's pulled 3 centimeters downwards and upon release oscillates up and down with an angular frequency of 9.1 radians per second. Calculate the magnitude of the velocity of the toy after 3.4 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, as it's being released for maximum displacement, we can use x equals a cos omega t. So it's 0.6 times by cos 9.1 times by 3.4, which equals 0.0533 meters. That is x. So you can then pop that into the equation of v equals omega times by the square root of a squared minus x squared. Pop in all the values there, so we therefore get 0.25 meters per second. The next question says, a pendulum bob is in simple harmonic motion with a period of 0.60 seconds and an amplitude of 5 centimeters. Calculate the frequency of the oscillations and the maximum acceleration of the bob. So pause the video now, then unpause the video when you want to go through your answer. Well, we know firstly frequency is 1 over time period, so therefore f is equal to 1 over t, so it's 1 over 0.6, which is 1.7 Hz. We then know omega is 2 pi over t, so it's 2 pi over 0.6, so it's 10.4 radians. So this allows us to then work out what our acceleration is, where acceleration is negative omega squared x, where we know omega is going to be minus 10.4, and we know that x is 0.050 centimeters into meters. So we get our answer out to be minus 5.5 meters per second squared. The next question says, state the defining equation of simple harmonic motion. So pause the video now, then unpause the video when you want to go through your answer. Well, the defining equation of simple harmonic motion is always the acceleration equation. So the acceleration is equal to negative omega squared x. The next question says, explain what is meant by the negative sign in this equation. So pause the video now, then unpause the video when you want to go through your answer. The negative sign shows that the acceleration is always directed towards the equilibrium position and is in opposite direction to the displacement. This is what makes the motion oscillatory. The next question says, an object undergoes simple harmonic motion with a starting amplitude of 0.10 meters. An angular frequency of omega is equal to 4 radians per second. What is the displacement at time t equals 0.50 seconds? So pause the video now, then unpause the video when you want to go through your answer. Well, we know x is equal to a cos omega t, so we pop in all our values, we can therefore get minus 0.0416 meters. Again, remember, we use cos as we're starting from maximum displacement. The next question says, for an object with an amplitude of a equals 0.15 meters, an angular frequency 6 radians per second, calculate the maximum velocity. So pause the video now, then unpause the video when you want to go through your answer. So maximum velocity is equal to omega a. So that is 6 times by 0.15, so that's 0.90 meters per second. The next question says, for an object with amplitude a equals 0.15 meters and angular frequency is 6 radians, determine the velocity when the displacement is x is equal to 0.09 meters. So pause the video now, then unpause the video when you want to go through your answer. Well, we know v is equal to plus or minus omega times by the square root of a squared minus x squared. So therefore we can pop in all the values and work it through. Therefore we get our answer to be plus or minus 0.72 meters per second. So the following question says, two identical masses oscillate in simple harmonic motion on identical springs. Mass A follows x equals 0.12 cos 5t. Mass B follows x equals 0.12 sine 5t. What is the phase difference between the two motions? So pause the video now, then unpause the video when you want to go through the answer. Right, well, we know that cos and sine link together because we know that cos is going to be ahead of sine by pi over 2 radians or 90 degrees. So therefore it indicates to us that mass B will lag behind mass A by a quarter of a cycle or 90 degrees or pi over 2 radians. The next question says, two identical masses, mass A, which follows x equals 0.12 cos 5t, and mass B, which follows 0.12 sine 5t, which mass reaches maximum displacement first? So pause the video now, then unpause the video when you want to go through your answer. Now, since A uses the cosine function, it will start with its maximum displacement at t equals 0. Now, B is at its 0 displacement at t equals 0, so therefore we know that A must be at maximum displacement first, because it starts there. So let's now have a look at some assessment point questions. The first question says, a mass is suspended from a spring and set into vertical simple harmonic motion. The displacement of mass x from its equilibrium position is given by the equation x equals 0.040 cos 15t. State the amplitude and angular velocity of the oscillation. Include the units in your answer. Determine the period and frequency of oscillation. Show that the acceleration of the mass satisfies the equation a equals minus omega squared x using the given displacement equation. Calculate the maximum velocity of the mass. Determine the velocity of the mass when its displacement is 0.020 meters, and another identical mass is set into simple harmonic motion with a phase difference of pi over 2 radians compared to the first. Write the expression for the displacement of this second mass. So pause the video now, then unpause the video when you want to go through your answer. So in our first question, we can work out from the equation the amplitude and the angular velocity. So from the equation, A will equal 0.040 meters and angular velocity will equal 15 radians per second. We can then say t is equal to 2 pi over omega, so 2 pi over 15, so it's 0.419 seconds. F equals 1 over t, so therefore it works through to be 2.39 hertz. This next one, what we've got to do is we've got to take the equation x equals a cos omega t, differentiate it twice, that gets us acceleration, so it drops out to be minus omega squared a cos omega t. Therefore, we know a is proportional to minus omega squared x, so therefore it is satisfied. We know that the maximum velocity is omega a, so it's 15 times by 0.040, so it's 0.60 meters per second. The velocity just a given point is equal to omega times by the square root of a squared minus x squared. Pop in all the values and we get 0.52 meters per second. Now the last one, we know a phase difference of pi over 2 implies a sine function rather than a cosine function. So therefore we can change the equation to reflect that by saying it's equal to 0.40 sine 15t. The next question says, a small platform oscillates vertically with simple harmonic motion. A motion sensor records the vertical displacement of the platform as a function of time. The displacement is modelled by the equation x is equal to 0.060 sine 12t. State the amplitude and angular velocity of the oscillation. Determine the period and frequency of the oscillation. Show that the acceleration satisfies the equation a is equal to minus omega squared x using the given displacement equation. Calculate the maximum acceleration of the platform. Determine the velocity of the mass when its displacement is 0.030 meters. Then another platform undergoes identical oscillations but reaches maximum positive displacement 0.25 seconds after the first. Calculate the phase difference between the motions in radians. So pause the video now, then unpause the video when you want to go through your answer. Right, again, we can work out amplitude and angular velocity from the equation. It's 0.060 meters in 12 radians per second. Frequency is going to be equal to omega over 2 pi. So it's 12 over 2 pi, 1.91 hertz. Time is 1 over frequency, so it's 0.524 seconds. Next, we will take x and we will double differentiate it to turn it into acceleration. So we'll differentiate it twice. So it becomes minus omega squared a sine omega t. So therefore, it satisfies the equation a is equal to minus omega squared x. Our maximum acceleration is omega squared a. So it's 12 squared times by 0.060, so it's 8.64 meters per second. Our general velocity equation is omega times by the square root of a squared minus x squared. Pop in all the values and you work it through to be 0.62 meters per second. Finally, what's our phase difference going to be? Well, our phase difference is going to be equal to 2 pi times by the difference in the time periods over the general time period, or the difference in the oscillation, I should say. So it's going to be 2 pi times by 0.25 over the general time period, 0.524. So therefore we get 3 radians. The next question says, a body is moving with simple harmonic motion. State 2 conditions that must be satisfied concerning the acceleration of the body. A mass is suspended from a vertical spring and the system is allowed to come to rest. When the mass is now pulled down a distance of 76 millimeters and released, the time taken for 25 oscillations is 23 seconds. Calculate the frequency of the oscillations. Calculate the maximum acceleration of the mass and calculate the displacement of the mass from its rest position 0.60 seconds after being released. State the direction of this displacement. So pause the video now, then unpause the video when you want to go through your answer. Right, you've got to learn the 2 conditions of simple harmonic motion. Acceleration is proportional to displacement, and the acceleration is in the opposite direction to the displacement towards the equilibrium position. Frequency is going to be the 25 oscillations over 23 seconds, because how many oscillations are there per second? 1.1 hertz. The acceleration is equal to omega squared a, or 2 pi f squared times by a. So it's 2 pi times by 1.09 squared times by 76 times 10 to the minus 3 minus 3.6 meters per second squared. Now we can use the cos equation for displacement because it starts at maximum displacement. So therefore you pop in all the values and you get minus 4.31 times 10 to the minus 2 meters. Now because it's a minus, it tells you on the other side of the equilibrium position from when it started. It started when fully pulled down, so therefore being negative means it's above the equilibrium position or moving upwards. The next question says, 150 gram mass was hung from a spring as shown. The spring was extended by 7.5 centimeters. The mass was displaced vertically 3 centimeters from its equilibrium position and then released. The mass oscillated vertically. Explain why the motion of the mass was simple harmonic motion. Calculate the maximum velocity of the oscillating mass, and then explain why the maximum velocity of the oscillating mass decreased over time. So pause the video now, then unpause the video when you want to go through your answer. Right, so why is that simple harmonic motion? Well, there's always a resultant force that is proportional to the displacement from the equilibrium position, and this force and acceleration are always acting towards equilibrium. Now in this next question, we can work out the force, because we know force is mass times by gravity. So when we turn our grams into kilograms, we get 1.47 newtons. We know that the spring constant is equal to the force over the extension. We convert 7.5 centimeters into meters and we get 19.6 newtons per meter. We now know that the time period of a mass spring system is 2 pi times by the square root of m over k. Pop all the values in and we get 0.549 seconds. We know omega is 2 pi over t, so it's 2 pi over 0.49 seconds, so therefore it's 11.4 radians per second. We then know V max is equal to omega times by A, so therefore we work it through to be 11.4 radians per second times by 3 times 10 to the minus 2, which is 0.343 meters per second. Now in the final question, energy is transferred out of the oscillating system and this energy is dissipated to the surroundings because work is being done against these resistive dampening forces. The next question says, a young girl is swinging on a garden swing. You may assume the swing behaves as a simple pendulum. Ignore the mass of the chain supporting the seat throughout the question and assume that the effective air resistance is negligible. Calculate the distance from the top of the chain to the centre of the mass of the girl in the seat. Express your answer to the appropriate number of significant figures. To set her swinging, the girl in the seat would displace from equilibrium and release from rest. The initial displacement of the girl raised the centre of mass of the girl and seat 250 millimeters above its lowest position. If the mass of the girl was 18 kilograms, what was her kinetic energy as she first passed through the lowest point? And calculate the maximum speed of the girl during this first oscillation. So pause the video now, then unpause the video when you want to go through your answers. Right, so in this first one, what do we know? So, how do you answer this question? Well, in the first instance, what you've got to do is you must work out the time period of each oscillation. So when you do this and you work it through, you do 42 over 15, that gives us a time period of oscillation of 2.8 seconds. We can then use our pendulum equation to work out the time period, and well, from the time period to then work out what our length is going to be. Because you know t equals 2 pi over square root, so 2 pi times by the square root of L over G. So therefore we rearrange it, and L is equal to t squared g over 4 pi squared. So it's 2.8 squared times by 9.81 over 4 pi squared. So this tells us that we get our answer of L to be 1.9 meters. Now again, it should be given to two significant figures as you're given information in the question 15 and 42 of two significant figures. Now in our next question, we can say EK is going to be equal to the potential energy because they're going to transfer between each other. So therefore we can say the kinetic energy is equal to the mg delta H. So at that point we can then say it's 18 times by 9.81 times by how far it is up, which is 0.25 meters, so it's 44 joules. We can then say that's also going to be the kinetic energy. So half mv squared is equal to 44.1. So therefore our maximum speed is going to be 2 times by our energy over the mass. So you get 2.2 meters per second. The next question says, a grandfather clock uses a simple pendulum to keep an accurate track of time. The seconds hands of the clock moves forward exactly 1 second each time the pendulum moves from A to C, and another second each time it moves from C to A. Determine the length of the pendulum in the grandfather clock that would accurately tell the time. The average gravitational field strength at the surface of the Earth is 9.81 meters per second squared. The pendulum is lightly damped. As a result, the clock needs to be wound up once a week. Suggest one potential cause of light dampening in the pendulum. Explain why dampening does not affect the clock's ability to tell the time. Then a grandfather clock has a pendulum of length as determined in the first part of the question. It's then used to tell the time at the Earth's equator, where g equals 9.78 meters per second squared. The clock was set to exactly the right time at 1800 hours on Monday evening. So determine the time displayed by the clock at 1800 hours the following Monday. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one we know t is equal to 2 pi times by the square root of L over G. So we can rearrange that to put L is equal to t squared G over 4 pi squared. We know t, remember it's the time we're going from A all the way back to A, times by G, and we know 4 pi squared, so we get 0.994 meters. Now, what is causing the light dampening? Well, the light dampening is going to be caused by a dampening force causing energy to dissipate to the surroundings. So friction of the pivot's pendulum, the internal friction due to the tension in the string, and air resistance will cause energy to be lost to the system to the surroundings as heat. Now, dampening will not affect the clock's ability to tell time because the time period of an oscillation is independent of the amplitude. Now, the dampener will cause a reduction in the amplitude, but it would not affect the time period of oscillation to change. That's an important idea that you've got to understand from light dampening. It does not affect the frequency and time period. In our next question, we know t equals 2 pi times by the square root of L over g. We worked out L to be 0.994 meters. So we can pop it in t in to get 2.00306 seconds. So what that tells us is that for every 2.00306 seconds that passes, the clock moves forward 2 seconds. So by that logic, for every 1.00153 seconds that passes, the clock moves forward 1 second. Now in 1 week, there are 6.04800 seconds, 60 times by 60 times by 24 times by 7. So in this time, the clock will actually move forward 6.03874.52 seconds, which is 925 seconds slower than the recorded time, which is 15 minutes and 25 seconds. So therefore, the time on the clock shown at 1800 hours on the Monday will be 17:44 and 35 seconds, which shows the importance of why clocks always have to be calibrated. The next question says, during the final stage of a wash cycle, an undamped washing machine increases the rotational frequency of the rotating drum from 0 to 1,250 revolutions per minute. The rotating drum has a diameter of 35 centimeters. Calculate the maximum linear speed that the clothes in the washing machine could reach during the final stages of the washing cycle. Between the rotational frequencies of 600 and 900 RPM, the washing machine can be observed to vibrate. The amplitude reaches a peak at 750 RPM. Firstly, explain the shape of the graph shown. Newer models of the washing machine are heavily damped. Describe what you'd expect the amplitude profile to look like in newer models compared to the graph shown. And then dampening is incorporated into the design of many everyday objects. A set of supermarket scales is damped to reduce the variation in weight measurements when food is put on the scales. State and explain the degree of dampening that is most suitable for a set of supermarket weighing scales. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that Vmax occurs at 1,250 RPM. So therefore, the frequency is 1250 divided by 60 to get into seconds, so it's 20.8 hertz. Now, omega is 2 pi f, so we work it through to be omega to be 130.8996 radians per second. Now, we know that the radius of the circle is going to be the diameter divided by 2, so 0.175 meters. Now, V equals omega r, so it's 130.9 times by 0.175, which is 23 meters per second. Now, the graph can be explained as the rotation of the drum forces the washing machine to vibrate at the same frequency. It's a forced oscillator. So as this driving frequency approaches resonant frequency of the washing machine will resonate, gain more and more energy from the driving force, and cause the vibrations to increase in amplitude. Now, the newer model would have a profile which is flatter, which is less sharp, have a much smaller amplitude peak as the resonant frequency, as that's what dampening causes to happen to the oscillation amplitude. Finally, what dampening would you want? You would want critical dampening, as the amplitude of the variation weight measurement will be reduced in the shortest possible time to get back to equilibrium so you can make your measurement quickly. So that brings an end to our revision session today. If we've been successful and we've learnt in today's lesson, we should be able to answer A-level physics examination style questions, assess your understanding on A-level physics, and understand what topics you need to improve upon for A-level physics. So thank you so much for watching this revision session on further mechanics on the topic of simple harmonic motion for AQA A-level physics, which is part of paper 1. Thank you so much and have a lovely day.